The beauty of this distribution method is that the Germans themselves complete the sabotage network. Once components enter the repair supply chain, German quartermasters distribute them according to standard procedures, installing them in radar sets from Brest to Berlin, in communication equipment from Norway to Greece. Every German technician who replaces a failed valve with a sabotaged replacement becomes an unwitting accomplice in the operation. If you're finding this interesting, a quick subscribe helps more than you know. It allows us to continue bringing you these forgotten stories of ingenuity and deception from the Second World War. The operational impact begins manifesting in early 1943, though British intelligence can only track its effects indirectly. Reports from Signals Intelligence indicate increasing German frustration with equipment reliability. A decrypt reveals a Luftwaffe maintenance officer complaining that newly installed radar components are failing at unprecedented rates. Another intercept describes a U-boat returning to port after communication equipment failures, the submarine forced to abort its patrol when it cannot reliably receive headquarters transmissions. The psychological impact proves even more significant than the material destruction. German technicians, faced with equipment that passes all standard tests but fails during operation, begin suspecting sabotage from within their own organizations. Internal security investigations multiply as the Gestapo searches for saboteurs in factories and repair depots. Workers face interrogation. Production facilities endure inspections. Trust erodes between different levels of the supply chain as each suspects the other of incompetence or treachery. A particularly revealing decrypt from February 1944 shows German intelligence becoming aware that sabotaged components are circulating in their supply system, but unable to determine the source or extent of the contamination. Their response, implementing more stringent testing procedures, actually plays into British hands. The additional testing slows the repair and distribution system, creating bottlenecks that conventional sabotage could never achieve. Equipment sits waiting for components that must now undergo extensive validation. Repair times lengthen. Operational readiness rates decline. The Germans attempt their own version of component warfare, but with far less sophistication and success. German intelligence does develop sabotaged components intended for Allied use, primarily targeting resistance radio sets. However, their approach lacks the subtlety of the British operation. German sabotage components tend to fail too quickly or too obviously, often burning out spectacularly during first use, immediately revealing themselves as sabotage. This actually helps Allied resistance networks identify and eliminate German infiltrators. Anyone introducing components that fail so obviously becomes immediately suspect. The fundamental difference lies in understanding of the operational environment. British engineers designed their sabotage components to mimic the failure patterns of legitimate components operating under stress. A valve that burns out after 50 hours looks like a manufacturing defect or operational wear, not sabotage. The Germans, perhaps underestimating Allied technical sophistication, create components that fail so dramatically they can only be deliberate sabotage, defeating the entire purpose of covert component warfare. American intelligence services, learning of the British operation through liaison channels, attempt to replicate it but struggle with the manufacturing precision required. American component makers, geared toward mass production with looser tolerances, find it difficult to introduce defects subtle enough to avoid detection whilst being severe enough to cause certain failure. A few American-manufactured sabotage components do enter European supply chains, primarily through OSS networks in Italy, but they never achieve the systematic penetration of the British operation. The operation's true impact remains impossible to quantify precisely even now. How many German radar sets failed at critical moments because of sabotaged components? How many communication breakdowns during Allied operations stemmed from British technical sabotage rather than jamming or bombing? How much German industrial capacity was diverted into investigating phantom saboteurs rather than producing new equipment? What can be established is the operation's contribution to a broader campaign of technical warfare that complemented traditional military operations. Each sabotaged component represented a small victory, but thousands of small victories accumulating across the German war machine created operational degradation impossible to achieve through conventional means. The operation forced Germany to expend resources on internal security rather than production, on testing rather than deployment, on suspicion rather than efficiency. Documents released decades after the war reveal that some aspects of this component sabotage continued being developed into more sophisticated forms. The concept of weaponizing supply chains, of turning an enemy's own logistics against them, influenced Cold War intelligence operations. The techniques developed for introducing undetectable defects into electronic components found applications in peacetime industrial espionage and countermeasures. Several British engineers involved in the wartime operation went on to work in telecommunications security, applying their knowledge of how to sabotage components to the problem of preventing sabotage. Today, no examples of these sabotaged components survive in public collections, though rumors persist of specimens preserved in classified archives. The Radio Security Service files pertaining to the operation underwent extensive redaction before partial release, with key details about manufacturing techniques and distribution networks remaining sealed. Several participants in the operation took their knowledge to the grave. Bound by Official Secrets Act obligations they honored decades after the war's end. The warehouse in Buckinghamshire, where Reginald Victor Jones examined that sabotaged valve, has long since been demolished, replaced by a housing estate whose residents likely have no idea of the unusual warfare once waged from their quiet neighborhood. The factory in Henley-on-Thames returned to legitimate production after the war, its wartime role unacknowledged for decades. The engineers and workers who manufactured these instruments of silent destruction returned to ordinary lives, their contribution to victory known only to a select few. But somewhere in occupied Europe in the winter of 1944, a German radar operator powers up his equipment for another night of tracking Allied bombers. The set hums to life normally, all indicators showing proper function. Then, 57 hours after a technician installed a replacement valve during routine maintenance, a microscopic inclusion in the filament finally weakens enough to fail. The valve goes dark. The radar screen dies. The operator curses and reaches for his telephone to report yet another equipment failure, never suspecting that a British engineer designed that specific failure 2 years earlier, in a workshop 200 miles behind enemy lines. That's the genius of Operation Periwig and its associated technical sabotage campaigns. They didn't announce themselves with explosions or proclamations. They worked silently, invisibly, turning Germany's own supply chain into a weapon aimed at itself. In an age of total war, when victory required not just defeating enemy armies, but exhausting enemy industry and eroding enemy morale, these sabotaged components represented warfare conducted at its most sophisticated level. Destruction achieved not through force, but through deception, not through violence, but through the patient corruption of the machinery that makes modern war possible. The rain still hammers down on Buckinghamshire warehouses, but the kind of quiet, methodical warfare once waged from them helped ensure that Germany's machines would fail when it mattered most, sabotaged not by bombs or bullets, but by the trusted components that were supposed to keep them running. The autumn rain hammers down on a nondescript warehouse in Buckinghamshire as a middle-aged engineer named Reginald Victor Jones peers through thick spectacles at what appears to be an ordinary radio valve. It is October 1942, and this unassuming component represents something extraordinary. A weapon that will destroy German machines without firing a single shot, without dropping a single bomb, without requiring a single soldier to cross enemy lines. Jones turns the valve over in his fingers, examining the delicate filament inside. In a few months, thousands of these innocuous-looking devices will be scattered across occupied Europe, and when they're installed in German radar sets, aircraft instruments, and communication equipment, they will begin their silent work of sabotage. This is the story of Operation Periwig and the ingenious British campaign of technical sabotage that weaponized the very components Germany desperately needed, turning the enemy supply chain into a Trojan horse of their own destruction. What makes this operation remarkable isn't its scale or its immediate dramatic impact, but rather its elegant simplicity and the profound psychological warfare it waged. The British weren't just destroying machines. They were destroying trust, creating paranoia, and forcing the Germans to question every component in their vast military-industrial complex. In an era of carpet bombing and armored assaults, this was warfare conducted in laboratories and workshops, a battle fought with microscopes and circuit diagrams rather than rifles and artillery. The story of how Britain turned ordinary electronics into instruments of sabotage reveals not just technical ingenuity, but a sophisticated understanding of how modern warfare had evolved beyond the battlefield into the factories, supply chains, and maintenance depots that kept the German war machine functioning. The challenge facing British intelligence in 1942 is both urgent and seemingly insurmountable. Germany's industrial capacity remains formidable despite years of strategic bombing. Their radar systems continue to guide night fighters against RAF bomber streams. Their U-boats, equipped with increasingly sophisticated detection equipment, prowl the Atlantic. Their communications networks coordinate defense across occupied Europe. Every night, RAF Bomber Command suffers devastating losses, and every assessment of German capabilities shows equipment that should be degrading, but somehow continues to function with remarkable efficiency. The conventional approach to disrupting this machinery involves sending waves of bombers over heavily defended targets, losing aircrew at unsustainable rates to achieve temporary damage that German Gongrenes repair within weeks. The Air Ministry calculates that for every German factory put out of action for a month, the RAF loses approximately 30 bombers and 180 trained aircrew. Even the most successful raids achieve only temporary disruption. The Peenemünde raid in August 1943, despite being considered a triumph of precision bombing, will cost 40 bombers and still fail to halt V-weapon development for more than 6 weeks. But there's another problem, one that gnaws at British intelligence analysts as they study German technical capabilities. How are the Germans maintaining such sophisticated equipment when their supply chains should be under immense strain? Reports from resistance networks describe German quartermasters desperately seeking replacement components. Radio operators in occupied territories speak of constant equipment failures. Yet German radar continues tracking RAF bombers with unsettling accuracy, and German night fighters continue finding their targets in the darkness over the Reich. The answer lies in a vast network of neutral suppliers, black market traders, and occupied factories across Europe. Germany isn't just relying on domestic production. They're importing components from Switzerland, Sweden, Portugal, any neutral nation willing to sell. They're cannibalizing equipment from occupied territories. They're operating repair depots across Europe, constantly refurbishing damaged sets and redistributing components. This distributed supply chain makes it nearly impossible to disrupt through conventional bombing. You cannot bomb every electronics workshop in Europe. You cannot intercept every shipment crossing a neutral border. The network is too diffuse, too adaptable, too resilient. What British intelligence needs is a way to poison the well itself, to make the Germans fear their own supply chain, to turn every replacement component into a potential saboteur. They need a weapon that doesn't announce itself with explosions, but instead works silently, invisibly, creating cascading failures that appear random but are actually deliberate. They need to weaponize the very components Germany depends upon. The solution emerges from an unlikely collaboration between the Radio Security Service, the Special Operations Executive, and a small team of engineers at the Telecommunications Research Establishment in Malvern. Dr. Jones, who serves as Director of Scientific Intelligence, coordinates what will become one of the war's most unusual technical operations. The concept is elegant. Manufacture radio valves, capacitors, resistors, and other common components that appear perfectly normal but contain subtle defects designed to cause catastrophic failure after a period of operation. This isn't simple sabotage like contaminating a fuel supply or weakening a structural component. The components must pass visual inspection by trained German technicians. They must function normally when first installed, allowing time for them to be distributed throughout the German system before failures begin. And the failures must appear random enough to avoid detection as sabotage, whilst being severe enough to disable equipment completely. The engineering challenge requires extraordinary precision. A radio valve designed for sabotage might contain a filament manufactured with microscopic inclusions that will cause it to burn out after approximately 50 hours of operation. Long enough to pass initial testing, but short enough to fail during operational use. The inclusions are so small they're invisible to the naked eye, requiring microscopic examination to detect. Even under a standard magnifying glass used by German inspection procedures, they remain undetectable. Capacitors receive even more devious treatment. British engineers developed techniques to introduce tiny air gaps in the dielectric material, gaps so small that the capacitor functions normally at low voltages but fails catastrophically when subjected to the higher voltages encountered in transmitter circuits. A German radar set might operate perfectly during ground testing, then fail spectacularly during its first operational transmission, the capacitor literally exploding from the voltage stress. The manufacturing takes place at several clandestine facilities, with the primary production occurring at a requisitioned factory in Henley-on-Thames, disguised as a legitimate component manufacturer. Workers, mostly women with experience in radio manufacturing, produce these sabotage components alongside normal production runs. The integration is so complete that even many workers don't realize they're manufacturing sabotage devices. A slight adjustment to the filament winding machine here, a modified dielectric formula there. The changes are subtle enough to maintain plausible deniability. Production numbers remain classified even decades after the war, but estimates suggest tens of thousands of sabotaged components were manufactured between 1942 and 1944. Each component is marked with authentic-looking manufacturer codes copied from captured German equipment. Some bear markings suggesting they originated from neutral suppliers Germany regularly patronized. Others appear to be from German manufacturers themselves. Perfect forgeries down to the quality control stamps. Distribution proves as ingenious as manufacture. Special Operations Executive operatives working with resistance networks arrange for these components to enter the black market that supplies German repair depots. A contact in Sweden arranges for sabotaged valves to be included in a shipment destined for Germany, the components indistinguishable from legitimate Swedish production. A resistance cell in the Netherlands intercepts a lorry carrying replacement parts, substituting sabotaged components for genuine ones before allowing the shipment to continue. In Denmark, a sympathetic factory worker employed at a facility producing components under German contract arranges for sabotaged pieces to be mixed into legitimate production runs.